Welcome to This Explainer. Today we're doing something really cool. We are going to decode the physical universe around us by tackling some real Cambridge exam-style physics questions head-on. By looking closely at how these core concepts are tested, we're actually going to reveal the hidden rules of the reality we live in, from the everyday forces you feel acting on your own body, all the way up to the colossal energies shaping the entire cosmos. It's going to be a fun ride.
Okay, let's dive into this. Here is our roadmap for today. We're going to journey through 5 key areas: motion, forces and energy, thermal physics, the world of waves, electricity and magnetism, and finally, from atoms to space. Section 1, motion, forces, and energy. This is physics on the human scale. All right, to get our minds warmed up, consider this classic problem. Imagine a boy whirling a ball on a string in a horizontal circle right around his head. Suddenly, he lets go of the string. Think about it for a second. In which exact direction does that ball fly off? Does it keep curving outward? Does it shoot straight out from the center like a rocket? Well, the secret here is inertia. The ball actually flies off in a perfect straight line at a tangent to the circle. See, the only reason it was moving in a circle in the first place was the tension of the string constantly pulling it inward, what we call centripetal force. The absolute instant that force is gone, the ball instantly obeys its inertia and shoots off straight from that exact point. Pretty neat, right? Let's apply that logic to another everyday mechanical scenario. Just a falling object. Imagine a stone with a mass of 2.0 kilograms being dropped from a height of 4.0 meters. How much kinetic energy does it have right before it hits the ground? Well, it's just a clean transfer of energy. We take the mass of 2.0, we multiply it by the Earth's gravitational pull, which is 9.8 meters per second squared, and then multiply that by our height of 4.0 meters. Basically, that initial gravitational potential energy converts entirely into kinetic energy, giving us roughly 78.4 joules of energy right before impact. It's all just beautifully balanced accounting. Moving on to Section 2, thermal physics, the invisible movement. Now, what's really interesting about this slide is how it tests something you've definitely felt before. Consider this. In cold weather, if you grab a saucepan, the wooden handle feels noticeably warmer than the metal part. But assuming they've both been sitting out in the same cold room, they're actually at the exact same temperature. So why does the metal feel so much colder to you? It's because this question isn't actually about temperature, it's testing your grasp of thermal conductors versus insulators. Metal is an excellent conductor. It rapidly steals the thermal energy away from your warm hand. Wood, on the other hand, is an insulator, so the heat just stays in your hand, making it feel warmer. We can actually explain this macro stuff using the molecular kinetic theory. Imagine you have a fixed massive gas trapped inside a container, where the volume just cannot change. What happens if you raise the temperature? Well, heat is literally just microscopic movement. The temperature rises, which means the particles gain kinetic energy and start zipping around faster. Because they're moving much faster inside the exact same amount of space, they're going to crash into the walls of the container more often and with way more force. And the macroscopic result of all those tiny crashes? The pressure on the container walls increases. Section 3, the world of waves, how we go about transmitting energy. So we can generally model waves in 2 fundamental ways. First, we have longitudinal waves. Think of a coiled spring. If you push and pull one end of it, the coils bunch closer together in compressions and then spread further apart in rarefactions. They're moving back and forth in the exact same direction the wave itself is traveling. Sound works exactly like this. Contrast that with transverse waves, like water waves or light. Here, the disturbance moves up and down, completely perpendicular to the direction the wave is actually heading. And this brilliantly illustrates the inverse relationship between wavelength and frequency across the whole electromagnetic spectrum. On one end, we've got radio waves. These guys boast the longest wavelength, but the lowest frequency. But as we move down the chart, through microwaves and visible light, the waves get tighter and tighter. Finally, we hit gamma rays, which have the shortest wavelengths, but the absolute highest frequencies, meaning they are packing immense amounts of energy. Which brings us to Section 4, electricity and magnetism, powering the modern world. Let's look at a highly practical, real-world scenario you'd find drawn straight from an exam paper. You've got an electric kettle in your kitchen. It operates on a standard 230-volt supply, and it's rated at 3,000 watts of power. Now, to wire this thing safely, you need to choose the correct cable. Should the safe working cable carry 2 amps, 5 amps, 10 amps, or 15 amps? What do you think? Here's how we easily resolve this. Step 1.
Just recall your power formula. Power equals current multiplied by voltage. Step 2, we simply rearrange that to solve for the current we need. So, current equals our 3,000 watts divided by our 230 volts. The result? It comes out to roughly 13 amps. Therefore, obviously, a 10-amp cable would just blow a fuse or melt. You absolutely must select the 15-amp cable for safe working capacity. Honestly, it just goes to show that mastering physics is really just about logically applying the right formula to a real-world problem.
Let's move to and see how this builds into our final domain, Section 5, from atoms to space, the extremes of scale. When we zoom closely in on atomic decay, we find 3 main types of nuclear emissions. Notice the really fascinating trade-off here on the chart. Alpha particles have incredibly high ionizing power, meaning they easily strip electrons from other atoms, but because they interact so heavily with everything around them, their penetrating power is actually the lowest. They can literally be stopped by a piece of paper. Gamma radiation is the exact opposite. It has the lowest ionizing power, but the highest penetrating power, requiring thick slabs of lead just to block it. And beta particles? They sit right in the medium for both. Now, zooming all the way out from the tiny atom, we reach the biggest question of them all. What are 2 pieces of evidence which actually support the Big Bang theory of the origin of the universe? I mean, it's a massive, mind-bending question, but physics actually gives us incredibly concrete data to answer it.
So the crucial point is cosmic redshift. Just take a look at this staggering speed, 16,000 kilometers per second. Through redshift measurements, physicists can actually see that a distant galaxy is receding or moving away from Earth at this unbelievable velocity. Everything out there is moving away from everything else, proving without a doubt that the universe is expanding.
And to make sense of that crazy expanding speed, scientists use Hubble's law, which relies on this tiny, highly specific number right here, 2.2 times 10 to the negative 18th per second. This is Hubble's constant. It's literally the mathematical key that allows us to translate that mind-bending recession speed into a tangible physical distance, measured in millions of light years. It bridges the gap between the velocity of a galaxy and its distance from us, basically offering a mathematical snapshot of the Big Bang's ongoing echo. And honestly, that is the true beauty of physics. From the predictable, everyday arc of a falling stone to the invisible buzz of gas particles heating up your kitchen, all the way to a distant galaxy racing away at 16,000 kilometers per second. The exact same physical laws govern everything. By decoding these concepts, you aren't just memorizing facts for an exam, you are literally learning the source code of reality. So my final question to you is, what physical forces will you decode next? Thank you so much for exploring the physical universe with me today, and keep questioning the world around you.